So in what follows, we want to find good degree distribution polynomials lambda offset and rho offset. Before we can do that, we need to look a little bit at some previous conditions, and we start with the first condition for the gap to capacity to see a little bit of what range of parameters we need to sweep, and then next one is a so-called stability condition. So the goal is to find the best possible lambda offset and rho offset, given of course some constraints. The first thing we do is we find a condition on the average variable node degree and the average check node degree. Afterwards, we show a stability condition. Then in the next video, we will show how we can use linear programming to find the best lambda offset and rho offset. Once we have lambda offset and rho offset, then it's very easy. Then we calculate L offset and R offset. And once we have L offset and R offset, we can get capital lambda offset, P offset, and construct the tenor graph. And by having the tenor graph, we have the parity check matrix, and we have the code. So the first thing we are looking at is the so-called gap to capacity theorem. So the theorem says the following. So we have an irregular LDPC code that has degree distribution specified by lambda offset and rho offset. These are the degree distributions from an edge perspective. And then we say we have a positive number epsilon tilde such that epsilon tilde times lambda of 1 minus rho of 1 minus xi is smaller or equal than xi for any xi between 0 and epsilon tilde. What does that condition mean? That condition simply means that our code is converging. So this means that this is the update equation. We start with a sum xi. We have the update equation. The update equation is smaller or equal than xi. So we are converging. So, and then we have a condition on epsilon tilde. It means that epsilon tilde should be smaller or equal than this expression, which purely depends on the average degree distributions of our code. Average variable node and average check node degree distribution. And this is actually a very simple equation, and that gives us a condition for the best possible epsilon. So it means that if we fix our average degree distribution, we have a condition onto what epsilon we can at most converge. The proof of this theorem is a little bit technical, but it's extremely elegant. So I refer you to the supplementary material, and you see that it's an extremely elegant way of proving it. It's not something you cannot do. It uses simple, very simple mathematical tools, the most complicated being Jensen's inequality. But besides that one, very simple and very elegant way of looking at the decoding problem. So what are the implications? So first implication is usually we fix the design rate. So if we fix the design rate and if we fix an average variable node degree, that means we cannot choose DC average. So we only have two free parameters, essentially one free parameter. So if we fix the design rate, then we can only choose the average variable node degree because the average check node degree will depend on the design rate. Now what we see is that if we let the average variable node degree go to infinity, which is what we have in the parity check code, we see when we make this parity check code very large, then the average degree will go to infinity. Sorry for this. So if we let the average variable node go to infinity, this term that looks rather nasty will actually converge to 1 minus the design rate. The implication for this is that we want to build capacity achieving codes. The average variable node degree should go to infinity. So here is an example. So here is the average variable node degree. We are looking at a code of rate 1/2, and we see the upper bound on epsilon tilde from the previous theorem. And we see that it will converge quite rapidly to the rate, to the 1 minus the design rate. And we also see that already for medium variable knot degrees, we will be pretty close to the 1 minus the rate. So it converges actually very fast. But in order to really achieve the capacity, so to get really to the final end, then we need to let the average variable knot degree go to infinity. But you will see that the difference becomes very small already quite early. So the next thing we're looking at is the so-called stability condition. So we start from the update equation. The update equation is simple. This one we know. So Xi is equal to epsilon of times lambda of 1 minus rho of 1 minus Xl minus 1, or f of epsilon Xi. We put an irregular here to emphasize that we are working with irregular. So now we expand f of epsilon Xi into a Taylor series around 0. So we say that Xl is f of epsilon 0 plus Xl minus 1 and the derivative of f of epsilon Cl with respect to Xl minus 1. Then we have some additional terms that depend on Cl squared, which we don't put in the series. So f of epsilon 0 is equal to 0. So if we insert 0 here, rho of 1 is equal to 1, 1 minus 1 is equal to 0, lambda of 0 is equal to 0. So this is equal to 0. And then we have this term, so it's the derivative is epsilon times lambda prime of 1 minus rho of 1 minus 0, because we look at the Taylor series around 0, times the inner derivative, which is rho prime of 1 minus 0, times Xl minus 1, plus the extra terms that depend on Xi squared. So this is actually equal to epsilon times lambda prime of 0 times rho prime of 1 times Xl minus 1 plus some term depending on Xi squared. So what does this tell us? Now we're looking at the when Xi becomes small. So when we are just about to finish decoding, we have already done some iterations and Xi becomes very small. So now Xi is extremely small. So, and then can we go the last mile essentially? So we have a small Xi, can we go the last mile to the very end? So if Xi is already very small, Xi square is negligible. We can forget Xi square. There's no Xi square we need to worry about. And the convergence is dominated by this term. Now we will converge if this term is smaller than 1. It's dominated by this linear term, this guy, and we will converge if this one should be smaller than 1. That's the condition. So the stability condition, we can look at what the implications are. So we start with lambda of z. So lambda of z is equal to lambda 1 plus lambda 2 times z plus lambda 3 times z squared, and so on. We have rho of z. Rho of z is, well, first, before we look at rho of z, we look at what we need here. So we need to take the derivative. So we take lambda prime of z. This is equal to lambda 2 plus lambda 3 times, so plus 2 times lambda 3 times z plus 3 times lambda 4 times z square, and so on. We're not interested in lambda prime of z, we're interested in lambda prime of 0. Lambda prime of 0 is equal to lambda 2. When we insert z equals 0, we just have lambda 2. Okay, so next we're going to look at rho of z. Rho of z is equal to rho 1 plus rho 2 times z plus rho 3 times z squared, and so on. rho prime of z is equal to rho 2 plus 2 times rho 3 times z plus 3 times rho 4 times z squared, and so on. We are interested in rho prime of 1, so we insert 1. To do this, we can have expression. This is the sum from j going from 2 infinity of j minus 1 times rho j. So that's rho prime of 1. So let's take a look at the case when we have a regular check not degree. So in that case, rho of z is z to the power dc minus 1. In that case, we'll have rho prime of 1 is equal to dc minus 1. Simply dc minus 1. Okay, so that is the stability condition that we have. And now we can take a look at these are the details that we have inside the stability condition. So now the stability condition says the following. So what I said already, we have convergence if and only if this factor that dominates the linear term is smaller than 1. And this means we have a condition on lambda 2. So lambda 2 should be smaller than epsilon times rho prime of 1. Lambda 2 should be smaller than 1 divided by epsilon divided by rho prime of 1. Or we can get an upper bound on the threshold. So an upper bound on the threshold is that epsilon star is smaller than 1 divided by lambda 2 divided by rho prime of 1. So what the stability condition says is that in irregular code, we get a condition on the number of degree 2 nodes. So it tells us how much degree 2 nodes we should have at most, such that the code will actually converge. Okay, so now we can go ahead and we could, for instance, start designing degree distributions such that we converge. Well, the easiest way to do this would be, for instance, just to select some lambda of z and rho of z such that the convergence condition is fulfilled mathematically or analytically. So what we do is we select lambda of z and rho of z. So for instance, I could start with some lambda of z equals to 1 minus z to the power alpha. You would say, okay, come on, this is not a polynomial. So what, how can I choose this? So this is something that doesn't look like a lambda of z that I should have. Well, I can use the binomial theorem to transform this into a sum such that it looks like what I need to have. So this is equal to the sum from j, and I call this lambda hat, from j going from 1 to infinity of alpha choose j times minus 1 to the power j minus 1 times z to the power j. And here alpha is an element of 0 and 1, and we choose alpha such that 1 over alpha is integer. So what is alpha choose I if alpha is not an integer, but alpha is between 0 and 1? That's a so-called generalized binomial coefficient. So alpha choose j is defined to be fraction of alpha times alpha minus 1, alpha minus 2, up to alpha minus j plus 1, divided by j faculty. So j is an integer, and we can divide by j faculty. That's a generalized binomial coefficient. So that gives us an operational meaning. So these guys determine the degrees. Because alpha is between 0 and 1, depending on j, you have either an odd or an even number of minus signs here, and that will be compensated by this minus. So this is just the binomial theorem. The 1 goes away. So we would start 1 minus this term starting at j equals 0. That is already being compensated for. It's the application of the binomial theorem, essentially. So then we can also determine an rho hat of z, which is just z to the power 1 divided by alpha, which we require to be an integer. So this is just a regular check node degree. So now we can look at f irregular epsilon c. This is equal to epsilon times lambda hat 1 minus rho hat 1 minus c. And we can just insert what we have now. So this is equal to epsilon times lambda hat of 1 minus c power 1 over alpha. And then we insert lambda hat. So this is epsilon times 1 minus c power 1 over alpha to the power, the whole thing to the power of alpha. And this is equal to epsilon times 1 minus. So the exponents, they cancel each other out. And there's a parenthesis missing here. So we have 1 minus c. And this is equal to just epsilon times c. So f of irregular epsilon c is equal to epsilon times c. And this will converge for any epsilon larger than 0 and epsilon smaller than 1. Because c is between 0 and 1. If epsilon is less than 1, this will always be smaller than c. So this will always converge until we reach 0. So this is a code that actually for every epsilon will converge. So what is the rate of the code? So let's calculate the rate. So the rate, design rate RD, is equal to 1 minus, that's the integral from 0 to 1, rho hat of tau d tau, divided by the integral of lambda tau d tau. So this is 1 minus the integral of tau to power 1 over alpha d tau, divided by the integral from 0 to 1 over 1 minus tau to the power alpha d tau. You can set that up. It's not a difficult integral. So we get 1 minus essentially alpha divided by 1 plus alpha divided by 1 minus 1 over alpha plus 1. And if you put this on a common denominator, do the cancelling, you will get 1 minus 1, that is equal to 0. So this is actually a code that has rate of 0. So it's not usable because you cannot transmit any information. So how can you solve this? Well, what is then usually being done is that instead of calculating a lambda hat, you will truncate this series at n. So we'll define some capital N where you truncate this series. Then you will need a normalization factor because then the summons will not sum up. The summons will not sum up to 1. If you let this go to infinity, the summons will actually sum up to 1. It's something you can prove. But then you truncate to n, you need some normalization. And then actually, depending on how you choose n, you actually get a rate that is non-zero. And you will keep this one. So you can twist the parameters alpha and n. You will end up with a rate that is not equal to 0. and you will have codes that actually have pretty good convergence properties, and they are called tornado codes. So this is one way of working with this. This has been proposed. This was more like a mathematical toy example. And this is not what we are going to look at. Now we are going to directly optimize lambda and rho, and that's something we're going to do in the next video. So next video, we're going to directly look at the optimization of lambda of z and rho of z.